Okay, there are some misconceptions out there about using the empirical rule and how it applies to different problem situations. So let's talk a little bit about that. Anytime you're dealing with the normal distribution, that means you have a curve that looks just like this. I'll even label it. It looks just like this. And you have two parts that will always, always, always appear on the normal curve. One of them is mu. This is the mean. The mean will always, 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 and forever occur right in the center of your normal curve. It doesn't matter what the numbers are. So if I stick some random numbers in here, maybe this is 5, 10, 15, 20, 25, 30, 35, just totally pulled those out of my head. That means with this set of data, 20 would be the mean. If I put in a totally new set of data, let's do 25, 50, 75, 100, 125, 130, 135. Another set of numbers I just pulled out of the air. That means the mean, the number in the middle, the long or the tallest line on that normal distribution would be 100, no matter what. So anytime you have a set of numbers applied to the normal distribution, the center number is always the mean, regardless of what it is. Now, I'm going to use the same set of numbers. Actually, I guess I could put them back. Pardon my repeated usage of the undo button to get me back to that original set that I made up. So now, the second part of the normal distribution curve that is incredibly important is sigma. This is the standard deviation. It does not mean you're the best. According to my 9-year-old, he tells me that that's what sigma means. This is the actual sigma. It is the standard deviation. Remember, the standard deviation tells you your distance from the mean. It is a measure of spread. So if I want the distance from the mean to each one of these values, I'm talking about this distance. Well, if I want to know how far it is from 20 to 25, I get a difference of 5. That means your standard deviation for the entire normal distribution in this case is 5. One of the ways you see this written a lot is you'll see mu in the middle. And then for the next standard deviation, or for one standard deviation past mu, you might see it written as mu plus sigma. Well, if our mu is 20 and our standard deviation is 5, that means the next jump over to the right from mu would be 25. To get another chunk of data in there, we write this as mu plus 2 sigmas, or 2 standard deviations away from the mean. So this is 20 plus 2 times the standard deviation, well, 20 plus 5 is 30, and so on. If you continue one more standard deviation out, this is mu plus 3 standard deviations from the mean. Now let's go backward. If it was 5 was our standard deviation on the right side of the mean, it's going to be the standard deviation on the left side of the mean. But to go backwards, instead of adding 5, we would subtract 5. So 15 would be the result of mu minus sigma. So our average was 20. Our standard deviation is still 5. We're just going to the left, so we subtract. So there's that next set of data. If we go backwards, one more. This is mu minus 2 jumps from the mean, or 2 standard deviations. My mean is 20. That hasn't changed. Standard deviation is still 5. Well, 20 minus 10 is 10. Same idea applies for the last section to the left of the mean. This is mu minus 3 sigma. So as long as you know mu and you know sigma, you can calculate the rest of these in your table. I'm going to clean this up a little bit. We'll take out some of my scratching. We'll take out the numbers. Because we cannot possibly make one of these tables for every possible set of data out there. Even if it was something I actually wanted to do, I couldn't do it. So I'm going to take these now. These are kind of my thinking steps. And I'm going to test it out with another totally made up set of data. So let's pretend that I tell you, I'm not going to tell you anything. I am going to make myself another set of data. I'm going to start this at 35. And let's do 42 and you'll bear with me, my caffeine has not kicked in. So I don't know what this is data for. I made it up. It came out of my non-caffeinated brain this morning. But let's see if we can come up with the mean and the standard deviation. Well, the way my table is set up, I still have all of the labels on there from last time, so I can apply these labels to tell me the information I'm looking for. My mean is always in the middle, so that means mu must be 35. The other thing I want to find out is the standard deviation. Well, standard deviation is how big the jump is from one section to another. So the difference from one section to the mean tells me my standard deviation. So that's how those work together. Now let's take a look at what this means as far as the empirical rule goes. I'm going to keep my same fake set of data right here. I'm going to change my highlighter color. Now here is what the empirical rule says. It says that when you have, that's going to be ugly. This is probably all going to be ugly. It'll be fine. But when you have a normal distribution, this distance right here between mu minus sigma and mu plus sigma. This is plus or minus 1 standard deviation from the mean. In any normally distributed study you conduct, 68% of the data will fall within these two numbers. So in this case, 68% of our data would be between my made-up 28 and my made-up 42. I don't care what the numbers are. I don't care what color you write them in. 68% of the data will always be in that blue area. Now, the next thing that the empirical rule states is that if we go out one section farther, Miss Graham, it really bothers me that you went outside the lines. I know it bothers me too, but not enough to fix it. It says if we add another standard deviation, so if we go and cover all of this green section, we are covering 95% of our data. So 95% of the data is going to be in our made-up set between 21 and 49, no matter what. Now this last piece, and I'm not going to color the whole thing because it's a little bit extreme. Oh, that is this skinny version. When I go out one more chunk, so I'm going to add these tails. And if you're going to make it ugly, you might as well go big or go home. So that purple part, from 3 standard deviations to one side and 3 standard deviations to the other, you are covering 99.7% of the data. That means you have 0.3% that's left in your little tails out here. That's how this works. Now, I'm going to clean this up one more time. we introduced this idea of z-scores to make this easier to label. When we put in z-scores, the z-score is the number of standard deviations away from the mean. All it does is it counts the sigmas. Well, mu, our average, doesn't have any sigmas. It has 0 sigmas, so its z-score is 0. A z-score of 1 happens because when we add 1 standard deviation, it's just like pulling off that coefficient from the sigma. It's actually a good way to put this. When we go out another step, we had 2 sigmas, so our z-score is 2. At the very end, our coefficient on sigma is 3, so we have a z-score of 3. When we go backwards, when we start to subtract sigmas, you get a z-score of -1, a z-score of -2, and a z-score of -3, because that's the number of standard deviations you are away from the mean on the left side. If we put this together with the empirical rule, this was 68% of the data between z-scores of -1 and 1. We have 95% of the data between a z-score of -2 and +2. And we have 99.7% of the data falling between -3 and +3 z-scores. Let's look at this with some data. So I'm going to put some numbers on here. I'm going to make them up. I'm not pulling these from any certain location. I'm going to just use one with easy numbers for the sake of my brain and its inability to do basic arithmetic this morning. Let's do 50, 70, 90, and 110. This might not work as well as I had hoped, but we'll see. 30, 10. I'm going to slide them all down. Maybe. I'm not. I'm going to erase them all. We'll start down here. 20, 40, 60, 80, 100, 120, 140. If you start at the beginning, it always works better. So, first thing I do when I see these is I write all over it. I don't even look at the numbers first. I label what I know. I know mu is in the middle. I know one jump to the right is a standard deviation. I know that the distance from 80 to 100 is 20. So my standard deviation is 20. If you want to be really sure, you're welcome to go backward and count that direction. The difference from 80 to 60 is still 20, even though we're subtracting, but that's okay. So I know my mu is 80. My standard deviation is 20. I also know that I can put in some z-scores. I know that mu has a z-score of 0. One standard deviation away gives me a z-score of 1. 2 standard deviations is 2. 3 jumps or 3 standard deviations from the mean gives me a z-score of 3. And I know that my normal curve is symmetrical. So if I can get one side, I can get the other. Now, let's say my question says, what percentage of data lies between 60 and 100? Well, I happen to have my handy dandy empirical rule chart, or my empirical rule. It says 68% lies with one standard deviation from the mean. So 68% of my data lies within 60 and 100. Now, what if I wanted to know the percentage of data that lied between 80 and 120? Well, Ms. Graham, I don't have that on my picture. You are correct. You do not have that on that picture. But what you do have is the ability to reason. Here's what we know. The empirical rule says that within 2 standard deviations of the mean, oops, that's not a percentage, you get 95% of the data. But I don't want the whole thing. I only want from the middle to the 120. The awesome thing about the normal curve is that it is symmetrical. So if you just want the percentage from 80 to 120, 95 divided by 2 will give you that percentage. Let's see. 45 times 2 is 90. 46 would be 92. 47 would be 94. So this is 47.5%, assuming my brain is sort of working. So this is how the empirical rule applies to stuff that you are going to see in your homework. See if this helps. Wrestle with it. Try to make it make sense in your brain. But if it doesn't, email me back.